Hello and welcome everyone to my channel Code with Ease. So as part of the sorting primer series, we are going to discuss about another sorting algorithm today. In the previous session, we talked about bubble sort algorithm, how it works, the overview of the algorithm. We also did a dry run on an example, and we also discussed the code implementation, both iterative way of solving, the recursive way of solving, and also the optimized way of solving it. So if you guys have not checked it out, I'm going to link it up above, and also I'm going to link up the playlists in the description, so do check it out. So today we are going to discuss about another simple sorting algorithm, which is called insertion sort. So similar to bubble sort, this is also a very simple and straightforward algorithm which works well for smaller data sets. And how it works is it's very similar to a game of cards, in which what happens is we initially consider the first card to be sorted, and then the other cards we consider to be unsorted, and then we try to pull out each card and put it in its correct position. So aligning with that, this algorithm also works something in a similar fashion. It tries to divide the array into two halves, sorted and unsorted, and it pulls out element from the unsorted space and tries to put it in the correct position in the sorted space. We're anyway going to see that in the upcoming whiteboarding session, in which we're going to see how this algorithm works. We'll also do a dry run on a given array example. This algorithm is actually best suited for arrays which are partially sorted, because as I told earlier, it tries to divide the array into two halves. So if an array is already sorted, so the number of swaps and trying to put element from an unsorted to sorted position, all of that logic, the number of comparisons and all of that becomes considerably lesser. As a result of that, this is good for data sets which are kind of sorted but not completely sorted. So with that, now let's move to the whiteboard to understand how this algorithm works. Then we'll do a quick dry run of that as well. Post that, we're going to see the code implementation, and at the last we are going to discuss about how the performance of this algorithm is, both in terms of time complexity and space complexity. So stay tuned. Hi, here's a brief introduction for the ones who are new to the channel. The objective of Code with Ease is to make problem solving in programming simpler. If you are someone who wants to become a great developer and wants to level up their skills, data structures and algorithms is indispensable, and you need to form a solid foundation of that. And this is exactly where we come in, because we post topic-wise video explanations in Java on various coding interview questions that can not only help to crack the coding interview, but also help to improve and refine the problem solving abilities as a developer. And finally, here is the USP of our channel. We code every solution live. We do not copy-paste code snippets. We start off by clearly defining the problem statement, the given inputs, the required output, time and space complexities. We also then discuss the brute force way of solving any question without jumping onto the solution, and then gradually move on to the optimal solution. We try to use online whiteboarding wherever applicable to explain the approach and the concepts. So that is all about us. So if you guys also want to be a part of this journey, do support us by subscribing to the channel. So with that, now let's get back to the question. So now we are going to see what this insertion sort algorithm is, how it works, and then we're also going to do a dry run on the sample array that I've taken. So like I discussed in my earlier video on bubble sort, it had a philosophy of compare and swap. That was the philosophy of bubble sort. Similarly, insertion sort algorithm also has a philosophy in which this array is divided into two parts. One is the sorted part and another will be the unsorted part. That is one thing. And every time an element is picked up from this unsorted part, and then it is put in its correct position in the sorted part. So this is the philosophy of insertion sort. First, dividing the array into two spaces, sorted or unsorted, and then picking element every time from the unsorted space and putting it in its correct position in the sorted space. So let's say, for an example, I have this small array like 1, 3, 5 and 2. Initially, just the first element can be considered as the sorted part, and the next three elements can be considered as the unsorted part. Now what happens over here is, every time from this unsorted space, elements is being put into the sorted space if it is eligible to be put. Like in this case, 3 is greater than 1, and if I have to sort any array in ascending order, it is fine. 1 and 3 are in the perfect order. Similarly, 5 is also in its correct position, but this element 2 is not in its correct position. So now this element has to be picked up from here, and then it has to be transferred into the sorted space. How it has been done is about the algorithm which we are going to talk about, but just giving you an overview of how it works. So now let's talk about the algorithm. What it does, first it will have one for loop to traverse from 0 to n, the entire length. Inside this loop, we'll also have another for loop which is going to start from index 1, and it will go backwards. Like if I say index 1, if I say j is the pointer, so I will say j equal to 1 and j will be greater than 0 and j minus minus. Why we are doing this, we'll come to this. Inside this inner loop, we'll have one logic. The core logic in this is the current element, if the current element, which is, let's say, ARR of j, if that element is smaller than the immediate previous element, that is j minus 1. So if this condition is true, there are going to be two things. One, put the current element, that is ARR of j, inside the correct position in the sorted space. We'll come to this in a little bit. I'll elaborate more on this. But if the condition is false, then we have to break the loop. Why? Like we said in this previous example, 1 and 3, 1 is fine, 1 is already in the sorted space because it's just one single element. 3 is in the unsorted space initially, and 3 is not lesser than 1, it is greater than 1. So in that case, I do not have to check any further, means this loop, this inner loop, need not go ahead and check any further. Or I can also say that, let's say I am at 5. So now 1 and 3 are already as a part of the sorted space. Now if 5 is greater than 3, means if this condition is not holding true, then do I need to check whether 5 is greater than 1 also? No, because 1 and 3 are already part of the sorted space. When I say sorted space, I am saying this array is supposed to be sorted in ascending order, so it's in increasing order. So if it is already in the sorted space and the current element is greater than the immediate previous, it need not go ahead and check it explicitly with the very first element and so on. So the same thing we are saying will break the loop, means this inner loop will no longer run all the way up to the 0 index. It will break. But if it is not so, like in case of element number 2, 2 is lesser than 5. So if 2 is lesser than 5, obviously 2 needs to come over here, 5 needs to go over here. But is that enough? 2 coming over here and 5 coming over here is still keeping the array unsorted. That is why 2 also has to be checked with 3, 2 also has to be checked with 1. So we have to go all the way to the beginning of the array. Now I will elaborate more on this. When I say putting the current element in the sorted space, by that I mean now ARR of j and ARR of j minus 1 has to be, firstly it has to be swapped, like in case of 2 and 5. So 2 and 5 has to be swapped. Now once that is done, this loop, this inner loop is going to continue. So now j will become like j minus minus. So then 2 and 5 is done. So now again 2 and 3 will be compared. Then they will be swapped. Then 2 and 1 will be compared and then they will be swapped if needed or whatever. So the idea over here is whenever this condition is coming out to be true, we are swapping j and j minus 1, and similarly we are letting the inner loop continue. So in that way, we are picking up element from the unsorted space and putting in its correct position in the sorted space if and only if that current element is lesser than the immediate previous element. If it is not, it will break it off. If it is, then it will swap and the inner loop will continue. This is the algorithm of insertion sort. Now let's do a dry run. Starting with the dry run for insertion sort. So this is the array that I have taken and I have spaced out the elements. So we are going to have two pointers. For the outer loop, we are going to use this I pointer, and for the inner loop, we'll use this j pointer. So the I pointer is going to run from 0 to n minus 1. Why is it so? We'll discuss that. And j pointer will be relative to I. It will be I plus 1. And j will be greater than 0. And also it will go backward. So j minus minus. So initially I is over here and j is here. So the comparison happens between j and j minus 1. So 9 is greater than 2. So therefore no swap will happen and I will move forward. So this will be I and j will be over here. Comparison will happen between 5 and 9. So 5 is smaller than 9 and that is why the swap should happen. So this will be 5 and it will be 9 over here. Now j will come one step behind. J will be over here. Now comparison between 2 and 5 happens. So which is fine, 5 is greater than 2, no swap is needed. J will actually be only till here, will not go any further because we are doing j greater than 0. The reason behind that is we are always comparing j and j minus 1th element. If we put j over here, then minus 1 element will be out of bounds. So that's why j will only be checking till over here. Now I moves forward. So this I will be over here and j will be here. Comparison will happen between 4 and 9. So 4 is smaller than 9. So swap should happen. This will be 4. This will be 9. Now j will come one step behind. So now comparison between 4 and 5 happens. So 4 is lesser than 5. So swap should happen. It will be 4 and this will be 5. Again comparison between 2 and 4 happens, which is fine because 4 is greater than 2. So now we have got 2, 4, 5 and 9 over here. Now I moves again one step. So I is now over here and j will be over here. Same thing, 3 and 9 is being compared. 3 is lesser than 9. So swap should happen. So this will be 3 This will be 9. Now j comes one step behind. Comparison between 5 and 3 happens. 3 is smaller than 5, so this swap again happens. So this becomes 3 and this becomes 5. Similarly, 3 and 4 is now being compared. Again swapping happens, so this becomes 3 and this will be 4. 2 and 3 comparison will happen, so it's fine. So now we have 2, we have 3, 4, 5, 9 and 6. I was over here, now I will be over here and j will be here. 6 and 9 is being compared. So 6 is smaller, so the swap happens. 6 will be here and there will be 9. 6 and 5 will be compared. 6 is greater than 5, so no swap happens. So the loop will break. And I will not go any further. Like I told, it will only happen from 0 to n minus 1 because j pointer is relative to I. If I put this I pointer at the last element, what will be j? It will be out of bounds. So that is why I will stop at the second last element and j will, when it is going backward, j will stop at the first element. Now this is the sorted array. We have 2, 3, 4, 5. Here we have 6 and 9. So yeah, that's all about the dry run for this algorithm. Now let's see the code for this. So now let's get started with the code changes for insertion sort. So first of all, we'll have this outer loop. I will be less than ar.length minus 1 and I plus plus. And this will be the inner loop. It's going to start from I plus 1. J will be greater than 0 and j minus minus. So inside this, we'll have this condition: if ARR of j is lesser than ARR of j minus 1 plus, then there's a need to swap. So we can write either we can use any swapping, either we can write the swapping logic inside a method and call that, or we can directly write it. I'll just write it directly over here. So this is the condition, else it's going to break. As we discussed, why is it going to break? Because if this condition does not turn out to be true, means that element ARR of j, the current element, must be greater than the previous element. In that case, we do not have to check with the previous to previous element. So we'll break the inner loop and we'll make the outer for loop run. So that's about this code changes. It's an in-place sorting algorithm. So we'll have to print this array itself. Let's run this. So here we have the result. Here's the negative number, which is at the beginning: 1, 2, 3, 4, 5, 8, 9, 18, 21, 22, 45, 89, 90. Yeah, looks sorted in ascending order, of course. So that's about the code for insertion sort. So now we are going to discuss about the performance of this insertion sort algorithm. 3 cases: best case, average case and worst case. In best case, it is order of n because best case will happen when the array is already sorted. In the first iteration only, every time the inner loop's check is going to happen and it is going to break out of it, and then the outer loop is going to run from 0 to n minus 1 and then it will be over. It is going to terminate over there because the array is already sorted. That is why it's order of n. In case of average case, it's order of n square. Average case is going to happen when the array elements are jumbled up. Some are sorted, some are not sorted. So in that case also, it has to go through all the 2 loops. So that is why n square. Worst case is going to happen if the array is sorted in reverse order, like if it is already sorted in descending order and we have to try to sort it in ascending order. So in that case, it is going to be worst case complexity. Same thing, both the loops need to run. That is why order of n square. And the space complexity is going to be constant. We are using an extra variable which is required for swapping. So that's a wrap on the insertion sort algorithm as well. I hope you guys have enjoyed this session. Do let us know in the comments below if you guys have any questions or doubts, or you want to share any feedback on this video. If you have enjoyed the session so far, do hit the like button so that this can reach out to many more people. And if it does, it just gives us enough motivation to put out more such content. Also, if you are looking forward to more videos like this, please don't forget to subscribe to the channel and press the bell icon next to the subscribe button to never miss an update on our upcoming videos. Thank you so much for watching.